Welcome back to yet another lecture of viscous fluid flow, where we are deriving the Navier-Stokes equation. So, last time we left at this particular point where we derived that the surface force is divergence of tau ij vector. So, proceeding forward from this point, it is important to note that this here the divergence of tau ij is also a tensor. Okay. So, as a result, Newton's law given by equation number 1 and 2 can be rewritten as rho dV dt is equal to rho g ij. Now, it remains only to, so there is another unknown term called tau ij, right. So, now it remains only to express this tau ij in terms of velocity v. Okay. Generally, it is done by relating tau ij to strain epsilon ij. Okay. You remember we derived epsilon ij in terms of the velocities in our first lecture of this module. So, it is relating tau ij to epsilon ij through assumptions of some viscous deformation rate law, which we have already done in the beginning. All right. Okay. So, before proceeding further, we will take a small detour and talk about a topic called hydrostatics. Okay. So, hydrostatics means fluid at rest, correct. So, we take a new page now and talk hydrostatics. So, from fluid definition, you remember the beginning definition: viscous stress vanish if fluid is at rest, correct. Velocity v and other shear stresses are 0 and the normal stresses become equal to hydrostatic pressure. So tau xx becomes equal to tau yy is equal to minus pressure. Tau ij is equal to 0 for I not equal to j. So this implies, if we put it in the equation number 9 that we have obtained, we become delta P equal to rho g. All right. If we assume z as upward direction, that means delta P will be minus rho g delta z. This is equation number 10. This means pressure increases downwards proportional to specific weight of the fluid, and this is a very famous equation that we know from before. So this was slight deviation, but we are going back again to the deformation for law for Newtonian fluid. Okay. So we are going to proceed for the further derivation of the Navier-Stokes law. Deformation law for a Newtonian fluid. So the idea was that we should be able to relate viscous stress to viscous strain. All right. So the simplest assumption for variation of viscous stress with strain rate is linear law given by Stokes. His three postulates are fluid is continuous and its stress tensor tau ij is at most a linear function of strain rates epsilon ij. Okay. The second postulate is fluid is isotropic, that is its properties are independent of direction and Therefore, the deformation law is independent of the coordinate axis. In which it is expressed. Third is when the strain rates are 0, the deformation law must reduce to the hydrostatic pressure condition. Tau ij is equal to minus p delta ij. Okay, here delta ij is Kronecker delta function, that is delta y is equal to 1 if I is equal to j and delta ij is equal to 0 if I is not equal to j. All right. So, this was his 3 postulates that Stokes said. So, this the last postulate is valid for the hydrostatic pressure condition. All right. So, we proceed and say, so his postulates are finished. So, we say let x, y, z be the principal axis where the shear stresses and shear strain rates vanish. Let's assume an axis x, y and z, x1, y1, yeah. So, instead of x1, y1 and z1 be the principal axis where the shear stress and shear strain rates vanish. With these axes, the deformation law could involve at most 3 linear coefficients C1, C2 and C3. So, example is, so if you want to write tau 11, it will be minus p plus c this we called equation number 11. Here minus P is added to satisfy the hydrostatic condition. Okay. Now the second postulate about the isotropic condition. Isotropic condition 2 requires that cross flow effect of epsilon 22 and epsilon 33 be identical, which implies C2 is equal to C3. This means that there are only two independent linear coefficients in an anisotropic Newtonian all right, where K is equal to C1 minus C2. This is equation number 12. We also know that epsilon 11 plus epsilon 22 plus epsilon 33 is, we have seen this for L derivation of continuity equation, divergence of V. So the next step is, so we have done this on an axis, I mean this terms which this terms we have written, we have done it on principal axis where the shear stresses and shear strain are 0. So there exist only normal stresses and normal strain, but now we have to transform it into an arbitrary axis where all the stresses and strain will exist. So let's transform equation number 12 to some arbitrary axis x comma y comma z where shear stresses are not 0. So earlier in the axis, the shear, we have assumed an axis where the shear stresses and shear strains used to vanish, but now since we have transformed into some arbitrary axis where these might not be 0. Okay. So if we are able to do that, this will give us a general deformation law. All right. So that is our next step to do. So with respect to principal axis x, y, z, let the axis so with respect to x1, y1 and z1, let the current x-axis, so with respect to the previous principal axis x1, y1, z1, let the current x-axis have direction cosines L1, M1 and N1. Let y-axis have cosines L2, M2 and N2, okay, with respect to the previous principal axis, and z-axis have cosines L3, M3 and N3, okay. We must also remember from trigonometry L1 square plus M1 square plus N1 square is equal to 1 and so on, okay, and this equation we called equation number 12b. All right. So based on this, the transformation rule between a normal stress or strain rate in the new system. Which is the new system? X, Y and Z axis, which is arbitrary, and its principal stresses and strain. Principal stresses and strain are tau xx, tau yy, tau zz, epsilon xx, epsilon yy and epsilon zz. Is given by tau xx is equal to tau 11 L1 square plus tau 22 M1 square plus tau 33 N1 square, and epsilon xx is given by same L1 square epsilon 22 L2 square L3 square, okay. So similarly, so this one equation number 13 relates the principal stresses. So similarly we can also relate shear stresses and shear strain rates are related to the principal stresses by following transformation law. That means tau xy can be written as tau 11, it is related to the principal stresses L1 L2 tau 22 M1 M2 plus tau 33 N1 N2. Similarly, epsilon xy is given as epsilon 11 L1 L2 plus epsilon 2 m1 m2 plus epsilon 3 n1 m2, and this equation we call as equation number 14. All right. So there are some things that you can try to find, which I expect you to do at your home, but if you have some problems we can discuss that in the forum. So two things try at home is use equation 12 and 12b to find the tau xx that we have written minus p plus k epsilon xx plus C2 divergence of v. Try to prove that. Okay. And secondly, tau xy is equal to k epsilon xy. All right. So this is equation number 15 and this is equation number 16. All right. So equations 15 and 16 are desired general deformation law. Okay. All right. So if by comparing 16 with shear flow between parallel plates, we say K is 2 mu. This we have done, we have seen before in our topic of laminar and turbulent flow. So K is equal to, and where mu is viscosity, and this is equation number 17. It is just by comparison. Coefficient C2 that we have mentioned before is independent of viscosity mu and is called as second coefficient of viscosity. This is also written as lambda, coefficient of bulk viscosity. All right. So equation 15 and 16 can be combined and written into a single general deformation law as for Newtonian viscous fluid tau ij is equal to minus p delta ij plus mu del ui del xj plus del uj by del xi plus delta ij lambda divergence of v. All right. Epsilon ij, if you remember, has been written in terms of velocity gradients. You remember our lecture 1? So, in lecture 1 we have derived this epsilon ij and epsilon ij, the shear strain rates, and we wrote in terms of velocity gradient. So, I think this is the nice and appropriate point to stop. In the next lecture we will talk briefly about the thermodynamic pressure and the mechanical pressure Stokes hypothesis, and then we finally write the final version of Navier-Stokes equation. So, that is enough for today, and I will see you in the last lecture of this module, which will be a brief one. Thank you so much. Have a nice day.